The project has already been introduced. It's been touched on a little bit. So I will skip that because Eric just spoke about that earlier, and I'll just start with the introduction to our scope of work on this project. So as Eric mentioned earlier, this is a pretty prominent church on the west side of South Bend. It really towers over the local neighborhoods. We were first asked to look at this project because there's vertical cracking running on all four piers on each tower, running up and down the tower. And it's at this point been repaired from the perspective of cosmetics and water infiltration. So it's not as noticeable, but I think before it was much more noticeable. But yeah, there's vertical cracks running running vertically. And it's a little bit alarming, I think, to any owner of a structure like this, and also a little bit mysterious as to why this happened. So that was the main focus of our investigation here. There's also some cracking at the east and west transepts on the pilasters there, which you can see in the bottom left photo. And then we also had some investigation on other parts of the building. We won't get into as much in today's presentation. So for the main issue, the cracking at the pilasters, we came in with a few different theories as to what that might be. The first, and obviously these different causes, it's not just one, two, it's a combination too. So one being thermal expansion. This church, or at least the bell towers, were likely built over the winter of, I think, 1926, if I have the year right. So the bricks themselves were at their coldest state and thermally would expand as the building heated up. They were also at their driest state, having recently come from a kiln, and clay masonry tends to expand over time as it acclimates to the ambient moisture in the area. Frost expansion, when clay masonry takes on water, it will expand as that water freezes during cold seasons. Rust jacking, something we'll talk on more, but if you look at the bottom center photo, there are steel columns embedded within the masonry, and when steel rusts, it expands and it exhibits a pretty substantial jacking force on the structure around it. It's something that's known as Regent Street disease, because there was a number of buildings built in, I think, late 1800s, early 1900s on Regent Street in England that all started exhibiting these same type of symptoms at the same time. Another potential cause was the use of Portland cement mortars instead of lime-based mortars. Wind movement of the tower was something that we added to our list of possible causes as we got further into the investigation. And one here I didn't list that we ruled out pretty quickly was foundation settlement. So for the methods of our investigation, we of course went there in person and did a field investigation, taking surveys, taking pictures, measurements, notes, etc. We did an historical record survey, which I always find to be a fun part of a project. I really enjoy studying history, especially local history. And this was a little bit of a small research project. We went through the parish records, kind of got a history of the building. We weren't able to uncover the original construction documents, unfortunately, even after checking with a few different sources like the diocesan records. But we did find a good trove of information, which I'll get into on the next slide. And that really involved, I think, Dov and I sat in the basement of the parish going through bins that hadn't been touched in 60 years, looking through different documents, but it was well worth our time. Analog and digital monitoring. So right here I have and you can also see on the lower left photo there on the screen, I have a digital displacement monitor, which just tracks displacement over time. We can set the frequency. I think on our project, we have the frequency set to every minute. And then we have analog crack displacement gauges too, which would be the lower right photo, which are only as useful as how often you go out and take measurements. And we, similar to the Matterport scan, but a little bit higher resolution, we did a exterior and interior 3D LiDAR scan. That's the photos you see on the top left and the top right. just showing a lot of the interior conditions. Obviously our scan focused on a lot of the structural spaces that aren't normally an area of investigation, such as the attic space above the main portion of the church and the bell towers. And then we were able to link those to get very accurate measurements of the building's geometry. And then lastly, mortar sampling. So we took some samples of mortar from different areas and had it sent out for analysis to confirm our hypothesis that mortars with high Portland cement content was used. Okay, getting into the kind of the history of the church. And I find on projects like these that you have to understand both the history of the structure and you have to understand the history of how buildings are constructed to really come to good conclusions on why a building might be having problems. The church was built in 1923, which is kind of an interesting period in the history of church construction in the United States, because we're transitioning from this older method of building. And I think the Basilica is a little bit of an example of that here at Notre Dame. If you look at the Basilica bell towers in Notre Dame, they have unreinforced masonry towers built with clay brick. And on the inside, they have essentially wood towers, which are hybrid of timber frame and steel connections to basically provide structure for both the bells and the stairway. And that kind of method of construction, this combination of timber and masonry, it was something that at this point had been proved over thousands of years. And at this point, we're switching to a new method, which is using a combination of steel framing and masonry, which is relatively untested at this period. So a lot of the traditional rules of thumb that were used in buildings of these types and proved over the ages have to be restarted with little experience. And in this structure, we start to see some of the problems that were not known at the time of construction. So this photo on the left here, that was one of the first photos we saw that I think the pastor sent to us, just showing, you can see the steel structure within the masonry towers. As we went through the historical records, one thing we realized is that these towers had been rebuilt not once, but twice due to the same problem we're seeing today. So they were built in 1952 by Schumacher and Sons, which was a local masonry contractor whose office was a stone's throw from our office in Mishawaka. And in 1963 by a more prestigious firm out of Chicago called Hoffer and Associates. Both are now out of business. We didn't want to follow either in the failure of the repairs or business models. So that was interesting to look at, because right off the bat, we're like, whoa, okay, this problem is not recent. It goes back 1952, essentially to within a couple decades of the construction of the church. And after two massive interventions, it's happened again. So I'm like, this deserves a pretty close and substantial study to figure out why this is happening. You can see in the 2000s, they did a more cosmetic repair just to seal up the cracks, paint them over so they're not as visible. Just anecdotally, another really neat thing about kind of diving into the local history of this parish and going through 100 years of box records is just the vibrancy of this parish and what this community looked like in the 20s, 30s, 40s, 50s. And it's just incredible. I mean, I think they have a memorial at the parish, and I think they had 46 men killed in action in World War II, which you're just like, wow, one parish in one small town in South Bend. And that's tragic, but also just shows like how many families were at these parishes, among which I think was Greg's father. Well, I don't know if that was his parish.
So my mom, so maternal side, my mom was a member of this parish. My grandparents, my grandfather died in 2006 at the age of 96.
Okay.
That's an example. And yeah, Polish, primarily Hispanic, 10% Polish, 90% Hispanic.
Mm-hmm. So yeah, just a neat story to kind of read about, when you see the 5,000 different clubs they had back then, and they all had a photo that looked like that. And you're like, wow, this is what people did before TV.
And I should note that, Bishop is connected with this parish because one of his questions always when he goes to a parish is, how many first communions and how many confirmations and how many marriages are there? And it's through the roof. of all the parishes in South Bend, this is one of the most vibrant. Now, St. Pius in Granger is probably more higher census and more confirmations and first communion, but for the existing parishes in the inner city, this one by far is the most vibrant.
So, yeah, that was just kind of the historical context, and with all of that in mind, we have these massive vertical cracks that haven't been solved. We have a couple of different theories. We laid the groundwork. We, installed monitors all throughout the church, especially in areas of kind of strategic concern. We brought in a consultant to do LiDAR scanning. And then from there, we started collecting data and analyzing the data. And I'll let David take over and discuss some of our findings. We're not 100% done with all our data collection. As of 1 week, we'll have been out there a year collecting data, and we'll also be getting the results from a structural investigation. They're finally digging into the piers at different locations. But yeah, I'll let David take over and discuss what we found from there.
Thank you, Joe. So as mentioned by Joe, our investigation, there is a reason why we wanted this one to reach this 1 year mark. It would represent a full year of seasons composed of different temperature. Of course, as mentioned before, one of our concern and the possible causes was temperature and expansion and contraction of the masonry. One more unexpected, I would say, cause that actually related very well with the readings of our cracks was wind. Wind, when you are thinking of masonry structures, wind is not the primary concern that you would have in mind. But remember that in this case, this is a masonry structure, true, but it got the aspect ratio more or less of a skyscraper. If you're looking at a bell tower in terms of footprint versus height, the aspect ratios are very similar to skyscrapers. And if you think of skyscraper, first and primary concern is typically wind. So we decided to include it as a possible cause for problems at the tower. And we actually found that correlating the data of our readings from the cracking measuring system with the data retrieved from a 10 years reading from the South Bend Airport gas wind station nearby, we found an extremely high correlation between the peak of wind gusts and the peak of our displacement due to opening and closing of the cracks. Together with a good correlation also with the thermal expansion, but the stronger correlation was actually the one we do. So now that we have this information, how do we apply our knowledge to solve the problem? Masonry, again, is a quite complex material on its own. Applying it to a church with these geometrical properties add complexity, of course, on the analysis of your structure. So our preferred way of modeling it would be a finite element model of the towers, in particular where the problems were focused. So thanks to the LiDAR scanning and the geometry that we accumulated, we were able to recreate a 3D model basically of the towers and the main facade of the church, as well as running more in-depth and more accurate analysis on what is going on. Before getting into the results there, I want you to remember that for a masonry design, a very important type of principle that should govern always your design is the box-like behavior. Masonry perform extremely well when you are tying the different walls together. If you are not tying the walls, or if you are losing this box-type behavior, your walls are going to perform as single elements and start buckling and not perform as a system. And it's very hard to achieve that type of behavior. Now, our proposed solution, thinking of the displacement and the stresses and the type of deformation that we have seen during the wind, was to reestablish this box-like behavior. As said before, there were some steel columns that were embedded in the corners of the church that surely didn't contribute in having a very well tie between the different wall of the towers itself, as well as the lack of effective horizontal diaphragms to restrain the embraced length of this wall, which again, we are talking of in the upper almost 200, I would say, feet, 160, if I'm not wrong. We are talking about 160 foot of length without effective restraining at any of the levels. The only restraining present there, which we do not call cannot call it a restraint, was the presence of some decks on wood joists that are not very well tied on roots. So our solution here, the proposed solution, was to reestablish this diaphragm action, reestablish this box-like behavior with the introduction of tension ties at different level of the tower. The shapes of an octagon there, which is quite artistic, is mostly driven by the presence of openings that you have to go through to access the different level of the tower. X-bracing would have been easier and surely would have brought less stress on the contractor and constructor, but in any case,
Which reflects in costs, right?
and reflecting
Yeah,
cost as well.
access to this.
But access
Tower is gonna be very difficult.
correct. Accessing the tower was one of the primary concern here, so we would have to deviate from the existing opening. Now let's look at what this type of solution bring in terms of analysis. Here I am showing a couple of pictures, one of our finite element modeling analysis pre-intervention and one after post-intervention. Now you can notice two things. These are the results of when we are applying a wind load on these towers, basically. You can see that without any sort of restraining and without an affecting diaphragm action, you have your planned cross-section basically warping under the effect of wind. So you are having extremely high concentrated stresses at the corners, and as a coincidence, but not that much, the corners are where the piers with the very long longitudinal cracks are. So imagine having this box that is trying to squish and open and trying to compress and torque those corners. Those corners are our piers. We have extremely long vertical cracks into it. This could be one of the major causes that cause that. Now, once we apply our diaphragms and our set of tension ties, the situation changes greatly. Now we are not having deformation anymore, or at least not as much. Of course, there is still some deformation. And our stresses at the corners are dropping significantly. Another problem that was addressed before by Joe was the presence of cracks at one of the transept of the church. Now, I have to imagine that this opening here is huge and is running all along the height of the transept. What is effectively creating on top of it is an arch. So when you have an arch in masonry, they are extremely valuable tools for designing. The Romans knew it well before us. They are extremely effective for design with masonry, but they also cause at the ends, at what are called the shoulders of your arch, they are causing very important and significant thrust forces, lateral thrust forces. Now the piers for how they were developed at the transept level, they were not either deep or thick enough or weight or have enough weight to counteract this type of thrusts, and that's why they started cracking. Now, to address this issue, of course, we cannot develop buttresses. That would have been how back in the days you would have handled this type of thrust. But we can act on one, reducing the demands. So try to reduce these thrust forces at the shoulders of the arch, and two, increasing the capacity of the piers themselves. To achieve that, on the back side of the wall, so inside the attic space, basically, we have devised a cold form steel truss attached to the back side of the wall to try to redistribute those trusses forces in more towards a gravity type of situation rather than lateral forces, and two, reinforcing the piers on the shoulders in a way in which we are reconstructing basically the masonry and adding anchors to increase the flexural and shear capacity of those of those piers. For solving another of the possible causes of our cracks and deformations and integrity issues that was mentioned again by Joe before, the rust jacking or the Regent's Street disease. What we are going to do, what we proposed and recommended is that to expose everywhere that we have exposed steel that is performing this type of rust jacking on the masonry. Rust jacking means that basically your steel is oxidizing, it's rusting. The rust is going to increase the volume and it's going to push on the masonry, generating the cracks. We are gonna basically expose them, clean off, grind off the rust, and apply a new coat of galvanization, basically. A post-applied galvanization to prevent the rust to come back in the future. This, of course, will increase the durability and the longevity of the steel itself, but at the same time, will prevent a new problem of rust jacking.
What shape are those steel members?
Those steel
Black
members
flanges?
were mostly white flanges, yes, correct. They were mostly white flanges embedded into. Interestingly enough, they were embedded up to a certain level. They were not embedded all the way through. So apparently it's like they changed their mind midway, which is never a good idea while you're designing. They started the construction of their towers in masonry, and then they reached the last level and they switched to steel. Most likely at the time might have been maybe easier, less heavy to construct in steel at those elevation, or it would have permitted them to have the very large and nice openings that you have. But that, of course, generate a lot of problems when you're trying to make interact two different systems.
So is it towers masonry, two-thirds, 1/3?
Two-thirds of the tower is basically masonry, and then there is a
steel.
transition to steel at the very last level and at the roof level. I think that
Shown in that photo.
it was showing a picture
Yeah.
before.
Yeah, right
Yes,
there.
right there.
So that's
That
where-
is more or less.
That's where the
exactly
steel
where
is.
the
The
steel is taking over.
steel doesn't go all the way down to.
Yeah.
Correct,
Great.
and that was another discovery in the field after drilling through
Yeah.
basically the piers and trying to find, okay, where is this steel landing? And this was actually one of the reasons why also the LiDAR scanning was extremely helpful in this case, because we were analyzing the geometry of the interior of the tower, and where the column was supposed to be, there was no masonry underneath anymore.
Yeah.
There was a conflict in the geometry of the masonry, and that what it was supposed to be the continuation of the steel column. So after this discovery, we actually went into the field, drilled into it, discovered that the steel is not there. It's not really
The
there.
steel's just resting.
It's just basically
slab.
resting.
Yeah.
Correct.
If it was done in today, probably would have put a slab and then bolted to it.
Yes, would have been probably better at that point, at least to give a closure to the masonry, because at this point you find yourself in a position in which you are completely losing your box-like behavior because you don't have a cap on your masonry, and now you're even restarting with a different system.
Yeah, it's basically built on a transfer beam, which is, it's all inset, and then that beam bears in pockets on the inside.
Transfer beams concrete or.
No, it's steel.
It'll be
Yeah,
steel.
it's steel.
Okay.
Oh, and I think we went a little far, but in any case, we reached the acknowledgement section, so. Let's restart from the end here. Among the various other entities, of course, Kill Architecture would like to thank for the collaboration and for the opportunity of this project. A member of the parish, Donald, and Father Ryan, extremely helpful, especially during the retrieval and the scouting of historical records of the church, as well as the Indiana landmarks, in particular the sacred places in Indiana. And we will now take any question you might have, and thank you very much for your attention.